Good morning, students. Today I am going to talk about spectral classification of stars. Now, the basis for spectral classification is mainly the temperature. Temperature, and you know how to measure, how to estimate the temperature of the star and their colors. And also, you know that there are absorption lines in the spectrum. The more hotter a star is, the absorption lines shift from hydrogen to the hydrogen helium line side. And for cooler stars, we will get spectral lines of molecules. So there are many spectral classifications, but most widely used spectral classification is the Hubbard spectral classification. We will use Hubbard spectral classification. This is Hubbard spectral classification. You know the name that it is done in the Hubbard. Hubbard. The most hottest star known to is called the O star. This is spectral class. First we write class. Most hottest is O star. Its color will be blue, and its BV parameter color index BV minus 0.3. Difference in magnitudes of blue color minus visual color. Visual blue color wavelength বোঝানো একটা visual color 550 nanometer আর blue color 35. Temperature, which is most important for this type of degree in temperature in the scale of 10 to the power 3. Okay. This is of the order of 25 to 50 kilo Kelvin. 25, 5,000 to 50,000 degree Kelvin is the temperature. So you can imagine the test body. This temperature is not in the interior. And absorption lines is it helium 1. 1 indicates it is it is neutral radiation absorption from neutral atom. Helium 2 means helium 2. This indicates absorption from a singly ionized. That means one electron of the helium atom has been ionized. This is called helium 2 line. In spite of that, there are carbon lines, carbon 3, nitrogen 3, oxygen 3, oxygen 3, silicon 5. These lines are there, but most prominent line is helium 1 and helium 2. This is the most prominent line here. Now, how can you know which is helium 9, helium 1 line, helium 2 line? For this, scientists have tables in which the wavelength of the absorption line have been specified. This has been found experimentally found in our Earth and atmosphere, and some lines have also been calculated using quantum wavelength or energy of the lines have been calculated using quantum mechanics, quantum theory, and others. And then the next spectral classification is P O D. Its color is also blue. Its color is also blue. Its PV index is minus 0.2. That means here the blue component is higher, here the blue component is lower. Its temperature is in the range of 11 to 25 Kelvin. And here the prominent absorption line, all the absorption lines present in the O class, here also hydrogen one line is also there, but very weak, very weak. Here helium 1 line is more stronger, helium 1 is more stronger, and other lines of this is also other lines also there, but here helium 1 line is stronger than helium 2. Now the example of these classifications, example of the stars that you see in the night sky. So for example, O type of star is Psi Par, means it is in the constellation of Perseus, and its name is Xi. Most brightest, generally the classification in a constellation of naming of the stars in a constellation is like that. Most brightest star is Alpha, then Beta, then Gamma, then Delta, and this goes. So this is a moderately bright star, Kuiper, and Gyurium. Gyurium in a Orion constellation. Gyurium. These are very easy. Most hottest stars and brightest stars. These hottest stars are also brightest stars because the surface temperature is very high, so they will glow like very. Their luminosity will be very small, very large because luminosity scale has actually about 4. So as temperature is very high, luminosity is also. So apparently the stars which are not so bright, not so bright are very not so bright are very very hot stars or very luminous stars. Their luminosity decreases because they are far distant. Now, B classification, this type of stars, example of this type of star is Vigil, Spica, Vigil, Spica. The next class is A. Its color is blue-white. Blue-white. Its BV index is 0.0. That means color index is 0. That's why তোমরা মনে করতে পারবে যে এর আগে যখন আমরা বলেছিলাম যে কালার ইন্ডেক্স যখন আমরা আলোচনা করছিলাম তাহলে এ স্পেকট্রাল টাইপের এই জিরো স্পেকট্রাল টাইপের কালার ইন্ডেক্সটা 0, এর কালার ইন্ডেক্স 0 and its temperature is 7.5 to 11 Kelvin. The spectral line that we observe for this class is hydrogen 1 is very strong, then calcium 2, neutral metal, H alpha, H beta, H gamma, H delta. These are also very strong, and neutral metal. Neutral metal means say calcium, sodium 1, neutral metal. Calcium 2 is distinguished as calcium ion. Now, example of this type star is one is Vega, That's why Vega has been taken as zero reference star in its apparent magnitude classification, Vega, and the other is Sirius A. Sirius A, the most bright star in the night sky, is in the spectral classification A. The surface temperature is 7.5 to 11,000 Kelvin. Next, spectral classification is F. Its color is white, white is yellow. Its color index will be 0.3. Means here visible component is greater. And its surface temperature, class of star surface temperature of a class star is 6 to 7.6 to 7.5 thousand degree Kelvin. And absorption lines, prominent absorption lines present here are calcium 2, calcium 2, iron 1, and others iron 2 are there, but this is just from this. Calcium 2 is the strongest line. Then spectral classification is G. Its color is yellow. Color index is 0.7. Now example of this cluster. F class example of this Tokyo. Tokyo is a star. 0.7, 0.7, and its temperature is 5 to 6,000 degree Kelvin. Our sun is in this category. Example of the star sun is one, and another is Alpha Centauri. Alpha Centauri. Alpha Centauri is the brightest star in the constellation of Centauri. So these are the G-type star. Prominent spectral lines are calcium 2 and neutral metal lines. Calcium 2 and neutral metal lines. Neutral metal lines. These are the prominent lines in G class spectral classification. Then the next spectral classification is K. K-type spectral classification. Its color is orange. Orange. Color index is 1.2. Temperature is 3.5 to 5,000 degrees. And prominent spectral lines are neutral metal TiO2, calcium 1, calcium 2, calcium 1, calcium 2, and this neutral metal. These are the spectral lines. Example of this is Arcturus. And the last of the Hubbard spectral classification is M. M spectral classification, whose color is red. Color is red. Color index is 1.4. its temperature is 2.0 to 3.5 thousand degree Kelvin, and its covalent spectral line is absorption line is TiO2. TiO2 is the molecule. Molecular absorption line is the strongest absorption line. Example of this is well-known Betelgeuse. This is the Betelgeuse is in the constellation of Orion. Is the right shoulder, star of the right shoulder of the Orion constellation. It is a red giant. Its radius is very much greater than the radius of the star, so its mass is comparable to the mass of the sun. So these are the main spectral classification. In addition to this, there are other spectral classification which are I'm taking very briefly, but these are not so frequently used. After that, K, E, C, and S spectral class. All these spectral classes are built in CS spectral classification are there. Their temperature is similar to that. Yes, say for example, C and S, C and S, C and S is in the C and S. This two spectral class is similar to M spectral class, and L and T spectral class, the surface temperature is mainly surface temperature is very small. For example, for L-type spectral classification, its color is brown. Its color is brown, and its temperature is nearly less than 2. And its absorption line is sodium 1, and 1. P spectral class is brown. Its color is also brown. Its temperature is 1000 degree Kelvin, and here the strong molecular absorption band CH4 and CH4 absorption lines of hydrogen molecule and methane molecules are there. These are brown dots. These stars are brown dots. Brown dots. They are very less luminous objects because their temperature is very small. So these are the spectral classifications. Now further, each group, say for example F group, each group, each class has been further divided into 10 classes from 0 to 9. From 0 to 9 is 10 for each class. Say for say M class. So M0 class is there, M0, M1, M2, M9. This is done because of the temperature variation. So this is hottest, and this is coolest. Means say temperature is 2 to 3.5, 2000 থেকে 3500 টেম্পারেচার, সারফেস টেম্পারেচার, তাহলে এইটা হচ্ছে 3500 হবে, আর এগুলো তার থেকে কম হবে, এটা 2000 হবে। তো এইভাবে আর প্রত্যেকটা ক্লাসিফিকেশনের মধ্যে 10টা ক্লাসিফিকেশন করা হয়েছে। এম এর পরে M9 এর পরেরটা কোনটা হবে? M9 এর যদি ফুলেস্ট হয় তাহলে পরেরটা হচ্ছে এল টাইপের স্টার হবে। এইভাবে আমাদের এই ক্লাসিফিকেশন গুলো করা হয়েছে। আবার স্পেকট্রাল ক্লাসিফিকেশন, এরপরে আমাদের যেটা যেতে হবে সেটা হচ্ছে ইয়ারকেস স্পেকট্রাল ক্লাসিফিকেশন। এখন ইয়ারকেস স্পেকট্রাল ক্লাসিফিকেশনটা কেন করতে হলো? তার কারণ হচ্ছে যে সেম টেম্পারেচার, একই টেম্পারেচার একই স্পেকট্রাল ক্লাসের মধ্যে থাকা স্টারগুলোর মধ্যেও তাদের লুমিনোসিটির অনেক ডিফারেন্স আছে। কোনটা লুমিনোসিটি বেশি, কোনটা লুমিনোসিটি কম। এখন এই লুমিনোসিটি ডিফারেন্সটা কিভাবে ভাগ করা যায়? তো দেখ, আমরা ডিফারেন্স গুলো বুঝতে পারবো। তো বেসড অন দ্য লুমিনোসিটি, here case classification was there. Luminosity, this was done by Morrison, Gilliam, and Gilman. Gilman in year case observatory. Year case name is in year case observatory. That's why this classification is termed as year case spectral classification. They classify the stars into this form. 1A, this is most luminous. Most luminous supergiants. Supergiant. Supergiant. It's most brightest stars, most luminous stars are called IA. IB, most luminous. These are less luminous, but they are supergiant. Yes. Then two, these are bright giants. Bright giants. Three, normal giants like Betelgeuse. Four, subgiants means subgiants. Giants means these are stars between main sequence stars and red giant stars. They are called subgiants. Then five, these are main sequence stars. Main sequence stars. What are main sequence stars? Will be clear very shortly. Then six, subdwarfs means these are stars between main sequence and white dwarfs. And the last class is D. This is termed as D or 7, that dwarf stars, white dwarf. The white dwarf, white dwarf stars. So these are the spectral classification. For example, our sun is G25 stars. G2b means its spectral classification is G2. G0 is most hot, G0, then G1, then G2, and its luminosity classification is B. That means it is the main sequence star. Now, another quantity of interest for this classification is the gravity, acceleration due to gravity. If you calculate the acceleration due to gravity on the surface of these stars, you will see that for giant stars, this value is very small, whereas for dwarfs and main sequence stars, this value is large. So we know acceleration due to gravity, acceleration due to gravity. G equals to Gm by r square, where m is the mass of the star, r is the radius of the star. Therefore, log G will be equals to log G ln. Better. Ln G equals to ln Gm by r. Now, if we calculate this thing, then for the stars, so for sun, this comes out to be this equals to ln G equals to 4.4 for sun. This is equals to 8 for Sirius A. I mean Sirius B, not Sirius A. Sirius B, which is a white dwarf. And this value is minus 0.6. Minus 0.6 indicates that this value is less than 1. This is the 0.6 for between is. So it is a superjet. Superjet. Any value less than 0 is called superjet. So between is a superjet. Now, based on this year case spectral classification, Hodgson-Russell diagram can be drawn, which I will discuss later after discussing the Hodgson-Russell diagram. So, spectral classification and luminous classifications are the classification based on spectral based on surface temperature of the star. Spectral classification is based on surface temperature of a star and their prominent absorption lines. And luminosity spectral classification based on the luminosity of the star, that means size of the star. Most luminous stars are massive stars and their size is very huge. Due to their huge size, their luminosity is greater, though their temperature is not so high. Next, we'll move on to Hodgson-Russell diagram. This is very important in astronomy and astrophysics. HR diagram is very HR diagram. Two scientists, Hodgson, E. Hodgson, E. Hodgson, and H. N. Russell, two scientists independently have done this work. So, in honor of their name, this classification, this diagram is known as HR diagram. What is this diagram? This diagram is a plot against luminosity or absolute magnitude. You know, luminosity and absolute magnitude are different. More luminous an object is, absolute magnitude, absolute magnitude will be negative, more negative. And versus its surface temperature or the spectral class. Now you have learned that surface temperature based on surface temperature spectral classification is there. So in the x-axis you can plot either surface temperature, you can the variable you can take as surface temperature or the spectral class. Now, actually, in 1914, the Russell drew a diagram which was like this. Here it was the spectral class, and this is absolute magnitude means M. Then he found, and the stars are plotted. He used four star clusters. One is these four star cluster, IDES. IDES, number two is Ursa Major, Ursa Major. Number three is Scorpius. Number four is 61 Sydney group. These four star clusters are taken, their spectral class is determined, their absolute value, their apparent magnitude and distance, their absolute magnitude is determined, and these are plotted. Here in the x-axis spectral class, first it is B, then A, then F, G, A, M, M. In the next class is L, and in this scale, this is the absolute magnitude. Say faintest are say plus 10 magnitude, plus 10, and the brightest minus 4 magnitude. 4 magnitude. They plotted this this band is called the main sequence stars. Main sequence, because most of the stars fall within this band. That's why he called it main sequence stars. And there are few stars below this band, below and above this band. The stars above this band are called giant stars. Giant stars. And the stars below this band, say these stars are dwarf stars. These are dwarf stars and these are giant stars. But their number is very small. Now, apparently, the cause for this was attributed, like, or the reason for this type of property of the stars was thought to be that the main sequence stars, the stars mainly spend their lifetime in the main sequence stage. And the end stage of a star is either giant phase or the dwarf phase. So initially, stars start their life cycle in a main sequence star form. Then after their as their fuel is exhausted, they enter into the giant phase. Then after some violent explosions or supernova explosion, their central the outer part is thrown out, the central part either become a star or a white. So these are the reason. Now the latter, when more stars were being categorized, property of the stars has been known, then a space-based satellite Hipparchus cataloged 22,000 stars, and they plotted and the HR diagram of these stars are something like this. HR diagram of Hipparchus effect. Telescope fitted in the Hipparchus satellite Hipparchus, they measured the luminosity, the parallaxes, and other just their absorption lines, critical plus of the stars, and if is plotted in HR diagram, where this scale is temperature is also equivalent to spectral plus. There it has been given by DV color index, DV color index, and this scale is L by L0. Luminosity L0 is the luminosity of the sun, and MV is the absolute magnitude. Is it magnitude? Absolute visual magnitude. L by L0. Say this is 10 to the power 10 to the power 4, 10 to the power 4 Kelvin. Say 6 into 10 to the power 3 Kelvin. Say 3 into 10 to the power 3 Kelvin, and so on. So, as in the case of HR diagram of Russell, here they found band like this. This is main sequence. Yes, main sequence stars. These are main sequence stars. These are giants. Very few stars are white. These are white. This class color of this star is blue, and color of this star is red. Our sun lies here. Our sun lies here. In this classification of focus 22,000 stars nearly. In this picture diagram, 22,000 stars are plotted. Most of the stars in the main sequence stars. Very few stars are in the giant phase, in the giant phase, and very few are white dwarfs. Because most of the stars spend their lifetime in the main sequence phase. The giant star belongs to the subsequent shorter lived part of the star evolution, and white dwarf is the last stage of sunlight. Thus, if star mass is comparable comparable to the less than sun, then it will be a white dwarf. Otherwise, their fate will be something else. So, this is the HR diagram of Hipparchus satellite. This also resembles the original HR diagram. Now, masses of the star and their lifetime in the main sequence have also been calculated by simulation method. And if we plot it in the, if you indicate their masses in the HR diagram, particularly in the main sequence stars, then we will observe that the apparent stars, say the stars in this category are luminous because the luminosity is high. So these are high mass stars. And the less luminous stars, so this type these are low mass stars. And our sun is low mass stars. Most of the most of the stars are low mass stars. High mass stars are very small. Another interesting thing is that low mass stars are numerous. We observe in the night sky and we can estimate their mass by various methods. How to estimate the mass we have discussed in various classes. Then we'll see that there are very few masses, very few stars which have mass, very large mass. This number is very small. Whereas the stars around the solar mass or less than the solar mass are very numerous. Now, why this is so? Then scientists realized that in fact the large stars or high mass stars spend less time in their main state. So based on this, if we draw a diagram, HR diagram, and indicate mass and lifetime of the stars, then it will appear something like this. Say this is the HR diagram, plotted E and L. So this is the main space. This is a 30 M0 mass star. M0 is the solar mass. Its lifetime is very small, 10 to the power 7 years. It is not so small, but small compared to the lifetime of sunlight stars. Then after this, say this is a 10 mass star, and the star Spica, I have discussed in the spectral classification. Spica is in the spectral class, Spica is the spectral class B. So D class, this is a star Spica, which has mass 11 mass of the sun. Solar. Then 6M, star of mass 6 times that of solar mass. Their lifetime is 10 times greater. So a 30M star has a lifetime of 10 to the power 7 years. A 6M star has a lifetime of 10 to the power 8 years. Then there is a star, say this is 2M. 2M below, there is a star Sirius, the brightest star in the Sirius A, which is twice M0. The mass of the Sirius is twice of the mass of the sun. And this is just 10 to the power, sorry, its lifetime is 10 to the power 9 years in the main sequence stage. Here our sun, his lifetime is 10 to the power 10 years. So it is 1000 times more than 30 mass star. Now our sun has the lifetime of 10 to the power 10 years. It has spent lifetime of 5 into 10 to the power 10, 5 into 10 to the power 9 years. 5 billion years is the age of the sun. It will go for another 5 billion years. And the very low mass stars, say 0.3 M star, M0, solar mass star, their lifetime is of the order of 10 to the power 11, 10 times greater. And brown dwarfs, which are very, very small, like Proxima Centauri. There is a star called Proxima Centauri. Proxima Centauri, whose mass is very small. Its lifetime is about 12 years. Means 1 trillion years, 1,000 times greater than the lifetime of the sun. So, in this diagram, what we see that the more massive a star is, spends less time in the main sequence, and the less massive stars spend greater time in the main sequence. Now, why this is so? This is because we know the stars glow due to the nuclear fusion happening in the interior of the star, where hydrogen atoms are fused and helium is produced. More massive stars, other nuclear fusion reactions are happening, where helium is fused and carbon, oxygen, nitrogen, these atoms are atomic weight uh, elements are produced, and this keeps on temperature of the star. The more for more massive stars, now the equilibrium, hydrostatic equilibrium of the star, what is happening there? The gravity of the stars push the star, material of the star into the center because the gravitational force is attractive force. And nuclear reaction, the energy produced in the nuclear reaction is keeping it in balance. That because due to the energy produced in the nuclear reaction, things are moving apart far away. So there is a pressure due to motion, thermal motion, and also there is radiation pressure. And these two pressure balances the gravitational pressure. Now, for more massive stars, the gravitational pull is very much. So to keep it balanced, the nuclear reaction rate has to be so massive stars has fastest reaction rate. I mean nuclear fusion reaction rate, so that their fuel hydrogen is used up very quickly. Whereas for less massive stars, very little nuclear fusion reaction, the rate of reaction is very slow. That's why they spend much more time in the main sequence phase than the high mass stars. So that's all about our first chapter, positional astronomy, in which first we have learned how to locate the position of a star. Then we learned how the different properties of star can be measured. That means its surface temperature, its luminosity, its mass, its radius, its distance. How this can be measured, we have discussed that. And in the last, what we have done after we have measured the absolute magnitude and apparent magnitude of the star, we came to know that apparent magnitude does not give the true luminosity of the star. The true luminosity of the star can be compared with absolute magnitude. And after absolute magnitude, scientists were physicists classified the stars into different spectral class depending on their surface temperature and their absorption lines that have been absorbed into the class. Among several spectral classifications, Hubbard spectral classification particularly mostly used, and have discussed this. Then after that, ear-case spectral classification is also discussed. That classification is discussed luminosity of the star. And lastly, we have discussed HR diagram, which is much more important in the classification of stars and properties of star in chart diagram, where we have seen that most of the stars fall in a band called the main sequence stars, and there are few stars above this main sequence, giant stars. Among the giant stars, there are also classes super giants, sub giants, some may be red giants. These classifications are there, and the stars below the main sequence are called basically white dwarfs or brown dwarfs. In the last, as I have said earlier, that the spectral hierarchical spectral classification can be plotted in the HR diagram also. This will be like this, somewhat interesting to you also, so that hierarchical spectral classification can be understood in HR diagram. From now on, the most important diagram that we have to remember is the HR diagram, and all the properties of a star can be understood in HR diagram. Say this is the HR diagram, temperature, luminosity. This is the main sequence line. So the lines parallel to these lines, you see, this is 5, 1A, 1B, 2, 3, 4, 5, 6, D or very interesting. So hierarchical spectral classification, when we see it in terms of HR diagram, looks like means the stars in this band are 1A, most supergiant, most luminous supergiants. These are less luminous, these are also supergiants. So these two stars are these are supergiants. Then come then comes bright giants, two types, 2 and 3, then normal giants, 4 are subgiants. These are stars in between giant and main sequence phase. And below the main sequence there is subdwarf and this white dwarf stars. Our sun is G25. Our sun is G25 star. This is our spectral classification of sun is. So our sun is in fact the middle of the classes of stars that we observe in our galaxy, Milky Way galaxy. Now, একটা জিনিস তোমরা এখন বুঝতেই পেরেছো হয়তো যে যে তারাগুলোর কথা আমরা বলছি, যে তারাগুলো সবই হচ্ছে আমাদের একটা গ্যালাক্সির মধ্যে আছে, যে গ্যালাক্সি আমরা মিল্কি ওয়ে গ্যালাক্সি। গ্যালাক্সির বাইরেও অনেক গ্যালাক্সি আছে, কিন্তু সেখানকার স্টারগুলো কিন্তু আমরা দেখতে পাবো না, অনেক দূরে আছে। যে গ্যালাক্সি আমাদের মিল্কি ওয়ে গ্যালাক্সির মধ্যে তারা নিয়ে আমরা এরপরে আমরা যেটা করবো সেটা হচ্ছে যে we learn about the Milky Way galaxy. What is the component, structural component and its properties of the Milky Way galaxy? Then we learn about the galaxies in general of the. Thank you.